Right, should we get started? Thanks everyone for coming to... Yeah, stop doing it. I'll just be your person. Thanks everyone for coming to this month's South East Centre Local Centre meeting. We've got a very exciting talk from Rosie in a second, but first we'll have Rob Thompson talking about weather summary 2024 summer and September so far.
So we're going for option. I will shut it because the people talking out there. So let's go. Please advance a slide. They may automatically go through these, but I shall do my traditional weather summary that I've been doing at the start of these meetings for a while, and start by looking at 2024 in Reading to date. So these are from my own little website that collects up the Reading University climate obs. So they're the manual red observations rather than the automatic ones. So it only does a few of them. But this was as of 10 a.m. this morning. Right? I grabbed that this afternoon. So if you decide that you're going to measure your calendar, none of this modern nonsense with marking off dates. You just measure rainfall and determine what date it must be from that. It was the 15th of December this morning. It's now next year, because you may have noticed that we've had more than 20 mil. If you click the link, Izzy, you can go. It will hopefully jump to a website that tells you it's still raining and we're now on 30 mil. We're now on 30 mil today. So you can go back now. I thought I'd better put that as a live link, because while I was writing this talk, I changed that number 7 times. So yeah, we have passed annual average rainfall today. Today was the day in Reading we passed annual average for the University of Reading field site. So we were going to be down by 6%, which is up by 42% for where you'd expect to be on this date. But I thought what I thought I'd do was actually compare to 2023 on the same date. Because actually, we're actually in a pretty similar position to what we were in terms of our annual totals and so on. Our temperatures, so basically you want to compare the bottom 2 rows. We're a bit warmer on T-maxes, on T-mins, slightly colder on T-max. T-means are therefore pretty similar. We're a bit wetter, but we're not enormously wetter, because last year was really wet, and both of our sunshines are pretty average. So actually, really similar to last year in terms of total, but we got there in quite different ways. Yeah, so the more than 20 millimetres from the last 9 hours does kind of change those numbers a bit, in that one is going to go positive. It might go to plus 1%, I think. If it keeps raining before 10 o'clock, we'll probably go to more than that. If we go on, I just thought I'd look at how wet it's been over the last, well, realistically, 2 years. It won't make any sense. So yeah, basically, it's been really wet for a long time. So over the last 25 months, this is the last 25 months at the university, 4 of them have been drier than average. Somewhat ridiculously, the 4th of those, the 4th month of the first of the 4, whatever, October 22, very average as well, really. So it was very, very close to being 3 of the last 25. 2 of the last 19 months were drier than average. What is, of course, quite odd is you do include February 2023 in there, which was the driest February we'd ever had, one of the driest months we'd ever had. And then that was followed by a March that had 3 times an average March and a bit more. So that happens. And this is just this year's rain total. So each month done separately, and then the annual total, with the black line being the long-term average by day. This little dashed line is when I sat down at 6:30 and I decided I'd move that little line up. That's my guess of where we're going based on today. So yeah, another chunk more, and you can just see we're just miles ahead of where you'd expect to be. And I guess if I continue this line out to December, it stops at about parallel to where it's gone to today. So yeah, really wet. But the funny thing is, because August and June were both quite dry, summer was dry. on average. We had a fairly dry summer on average. I guess you can see that in this period. There's not a great deal of rain in that bit, and the black line caught up a bit. But it very quickly became September, and that all went downhill very fast. So if we move on again, I thought I'd talk about something different and temperatures, because I talked about this in the spring a couple of times. The last air frost we had in Reading was the 4th of March, which means actually it sounds really silly, an early last frost. But that was the second earliest last frost Reading had had since the records begin in 1908. It was, yeah. So this was a chart I'd made in the spring of basically when's the last time it's that cold. As a gardener, this really matters to me. So put all the tomato plants out here in the desperate hope we'd have no frosts. And well, it worked out. So I made that plot back in the spring of when can I trust that it'll probably be safe to put tomato plants out? And well, I won. But it's worth noting actually, 25% of years in our record have a air frost in May, which surprised me. We click on. I did think, climate change is going to have changed that. So the solid lines are 1920 to 1949 averages, and the dotted lines are the last 30-year averages. I'm not convinced they're very different. That, I think, is the main point there. We don't really see -10 anymore. We don't really see -10 ever, so it doesn't really happen. The -5s do still happen, etc. So there's not much change really. If we go on, then we probably then this autumn got some payback for having a really early last frost, and I think it was the 12th of September. It was while I was in Italy it was boiling hot in Italy. I got a report from my allotment looker after that it had frozen on our allotment, and that it froze in the polytunnel and killed all the tomato plants, and everything has mould, and it's disgusting to come home from Italy with. But that's how it goes. But yeah, thanks to Stephen Burt, who pointed out that that was the coldest night in the first half of September since 1931. So quite a record there, really. It's almost 100 years to go that cold that early in September. And you can see it's miles away from the long-term averages and so on. So really very cold. If we go on again. I thought we'd look nationally at how wet it's been, because wet kind of is the message all year, really. And so I've gone winter, spring, summer. So it's not quite 2024, but it's most of 2024. So as we said, the summer actually is drier than average, but it does look really patchy. This looks more patchy than I think I'm used to when I look at the seasonal ones of this. And there are definitely areas that are going to be really, really wet for this year. The Lake District has been wetter than average all the time. Oddly, a little patch. Don't go to, this seems to be a case of don't go to Weymouth. It's wet, really wet, pretty wet. Well, yeah, just patchiness really. Also, the east tip of the east end of Scotland is very wet, but it's pretty much a wet picture nationally in the anomaly. Obviously, if I plot these out as the absolute rainfalls, what you see is really wet in the northwest of Scotland, so I tend not to do that. If we go on, I thought I'd just sort of see, because September's been really, really wet. I had 2 weeks in Italy, and going to Italy appears to have been, like Reading will now, well, everywhere in the UK really, would just suddenly turn into thunderstorms and rain all the time. It's odd because Italy also turned into thunderstorms and rain all the time, but mostly they dodged us, which was lucky. But it's been really, really wet in some places. It's been a lot of thunderstorms, and like the showers mean everything's really patchy. So thanks to Roger Bruges with his email the other day, just to demonstrate how patchy, on the 22nd, so Sunday, Reading 31.2 millimetres, 15 kilometres away in Maidenhead 93.2. So yeah, that's what, factor of 3 essentially difference in 15 kilometres, and like Reading at 31.2 is already one of the wettest days you get in most years. So basically crazy amounts of rain, and then this is just where the flood watches and warnings are. So Flood alert are the sort of amber triangles. Flood warnings are the red ones. We haven't got any severe flood warnings, which really tend to come when either the water's already out and in the sort of out of the channels and so on, or when it's just about to. So we haven't got that happening yet. But you can see a big patch through the sort of southern Midlands / northern southern bit of England here, and then there's another patch up in the northeast. If we go on, I thought I'd go global as well, because there's been a lot of stories, some stories that made a lot of impact really in newspapers and so on the fact that firstly, in July, we had the hottest day on record. We probably then the next day had the hottest day on record, because we had 2 in a row that broke the record. The second one was a chunk warmer than the first one in terms of actually 0.06 is quite a big difference in terms of how these vary. And this is just a chart with every year since 1940 and then the last 2 years coloured in. Obviously, I stole this on fairly near the date I nabbed this clock from. But you can see really clearly that this big, and 2023 and 2024 were miles ahead of anything we'd had previously as well, which obviously we're going to say climate change, but also we're going to say El Nino. So if we click on the next one, that's sort of relevant here because it's also almost certainly going to be the hottest year on record. So this is going back for the temperature anomalies. This is where we're looking for the summer, this one, and so we had the hottest summer on record globally. So they based this off the era 5 temperatures globally. So it should be, I mean, different ways of doing it score slightly differently, but they'll all be pretty similar. So exactly whether 2024 will be 2023 will depend which data set you use. I imagine they won't all be out yet, certainly, and but they're both miles clear of the others. It's almost certainly going to be more than 1.5 degrees above the pre-industrial average. Basically, to not be is going to require a cooling of the entire globe that's sort of more drastic than has ever happened in the past. So it essentially certainly will break the 1.5 degree threshold again. But the important thing really is that the El Nino is over. And we are starting to think about entering La Nina. So this is where we are roughly, the orange line of so this is 3.4, Nino 3.4 index, where we're forecast to go. So we're forecast to be basically over the autumn, going into La Nina. And we have pretty much been tracking to neutral conditions for a while now. We are in the neutral. So that probably means next year won't be so hot, because El Nino does produce higher global average temperatures. So I think that's my last slide. Yes, it is. Yep. I think that's a good summary, really, of where the weather's been this year. Locally, very wet and a little bit warm, but so much a little bit warm that it actually felt cold because we're so used to it being a lot bit warm. And yeah, just incredibly wet, and with not really a great deal of sign of that stopping. So with that, I shall pass over to our speaker, Rosie Mamat, who is from the University of Reading. You are going to talk about characterising ice particle size distributions, and I definitely can't speak tonight. I have had one of those days.
Well, that's a bit more interesting than my actual title, anyway. I also am missing a stick, so you're just going to have to deal with my arm waving, I'm afraid. Okay, yeah, so for those of you who don't know me, as Rob said, I'm Rosie. I'm a second-year PhD student here at the University of Reading, and this is my PhD work that I've been doing with my supervisors, who are listed here, 2 of which are from Reading and 1 from Manchester. Are you clicking for me? Is that how this works? Okay, next slide, please. So, a bit of an introduction. Clouds play a very important role in the weather and climate system at the Earth's surface. So accurate forecasting of clouds is important for both numerical weather prediction and climate models. So accurate representations of clouds and their processes rely on accurate representations of the particle size distributions in the cloud. And this affects like what we feel on the surface. So Process rates being sort of whether it's raining. So if you go to the next slide, please, Izzy. Precipitation of formation of precipitation and the radiative effects of cold clouds. So that's how much heat they are trapping in or conversely letting out. So models are increasingly moving towards a double moment microphysics scheme. I'll explain a bit more about what that means in a bit, but what it means basically is that number concentration and the mass of ice in the cloud are forecast variables that they then use to work out the particle size distribution. And then to calculate the process rates, we need a parameterized PSD. And for this, most models use an exponential or gamma function. Again, I'll explain a bit more about that in a bit. And in this talk, we are going to focus on CASIM, which is the UK Metal Physics Next Generation Microphysics Scheme. But the findings we find would apply to any gamma PSD because it's just about finding the right shape parameters to use for that gamma distribution. So next slide, please. So also a little bit of motivation. Why is snow important? This is a really nice figure I've taken from Field and Hamescale paper. And this shows the fraction of rain events that start as melting snow. So what this means is that the precipitation, when it falls from the cloud, is frozen precipitation and then melts as it reaches the ground. So you can see, as you would expect, a lot of the precipitation at the very southern and very northern latitudes starts as snow. But you can also see over huge regions of Asia and Europe and North America, and also huge regions of Africa, where that's desert, so you wouldn't expect that. Then compares to the fraction of precipitation events that are still snow by the time they reach the ground, where that's very concentrated to this southern hemisphere and the very northern latitudes, Greenland, and then you've got a little bit up the Andes there as well. So it's not just limited to the outside of the tropics. This is a global problem. So next slide, please. So I'm going to just talk a little bit about the data and instrumentation that we are using for this study. So next slide. The data I'm using is coming from the Picasso field campaign. This was conducted in 2018 to 19 by a team from the Metal Phys, Manchester and Reading. And they used aircraft data and radio sondes and radar to collect their data. So we've got the Facility for Atmospheric Airborne Measurements, did I get that right? I think so. Which is this aircraft here, which is equipped with all sorts of instrumentation for measuring temperature and wind speed and pressure and some specific ice things, which I will talk about in a sec. We've also got radio sondes that were launched from Chilbolton. This is actually a photo from Westcom, but it's a radio sonde. And I'm using the temperature data from the radio sonde because there was a fault with the one on the aircraft. And then we've also got co-located radar and aircraft measurements, which is very cool because then we can compare those two. So next slide, please. So a bit about the instrumentation. These are some example images from some of these probes. And then this is where the sort of probes are situated on the aircraft. They hang down below the wing. So we're using optical array probes, which use lasers to capture 2D binary images. So what this means is they have two arms, and then there's a laser between them, and it basically measures out the black space in that laser caused by a particle going through it. So we've got a few of those which measure particles of different sizes. So we've got one that does the very small stuff up to about 1 millimeter, one that goes up to nearly 20 millimeters, which sounds big, but is still tiny. And then we've got cloud imaging probe. I'm not using that one too much, but that's what this image has come from. And then we've also got the cloud particle imager, which is what produces these amazing images. And this is where you've got a little tube under the aircraft, and as it flies along, it collects individual particles, which are then lit up by a laser, and then a camera takes a photograph, which I just think is amazing. Yeah, okay, I think that's what I wanted to say about that slide. So next, please. So this is the case study we are focusing on for this study. So it's a large frontal cloud. This is an image taken by the radar at Chilbolton, and this is the one where it just sits and points, looks upwards all day. So this is like the evolution of the cloud over that space with time. And in the black box, that's the time of the aircraft flight. So the aircraft would have been going through this cloud, and you can see here like the melting layer. And this is the base of the cloud then, because when you see the entire reflectivity values, that's where it's raining. Yeah, so this is the front indicated here that caused this big cloud. Next slide, please. And this is what the aircraft was doing during that flight. So it was doing runs at different altitudes here along this part of southern England. I'm going over Chilbolton so that they could get those co-located radar and aircraft. And then it was doing all of these at different temperatures. So this is sort of, these indicate where it's gone over Chilbolton. So we're not using all of these runs, but most of them. Some ended a bit short, some went a bit wiggly. So we've kind of picked the best examples from there. Next, please. Okay, so that's the sort of observation side of it. Now I'm going to talk a little bit about the model side of it. So next slide, please. So there's kind of two types of models I'm going to be talking about today. And the first one is a single moment scheme. So most operational forecast models use a single moment scheme where only the mass of ice crystals is a forecast variable, and then the number concentration of particles is fixed according to temperature. Next slide, please. Oh, no, yeah, that. But is this a good enough representation of the number concentration of particles that is observed in a real cloud? Because this is quite an important issue. Next, please. As XKCD expertly shows, if you've got one giant water droplet, that's all the mass in your cloud, that's quite a problem for your people on the surface. Whereas if you've got really fine rain that just goes on for a while, that's got much less impact. So it's quite an important thing to know. So next, please. So we're sort of making the shift to double moment schemes. Climate models have actually been using these for a while, but operational forecasting models have sort of taken a bit longer to get to this point. So they use particle concentration and the mass to predict the PSDs, which means we can get a much more accurate representation of the particle sizes that then feed into the PSD. So in a lot of these, it's described using gamma distribution, such as in Kazim, and that's what I'll be talking a bit about now. So next, please. Okay, this should have been before, I guess. But many operational models, including the current Met Office model, use an exponential distribution. But is this actually a good enough representation? Next, please. We've decided it's not, so we're sticking with this gamma. But in the literature for a long time, that exponential distributions have been used to represent particle size distributions, not only in forecast models, but also in remote sensing retrievals. So that's something we'd like to sort of investigate a bit more in the future, but more about that later. Next, please. So we use the gamma distribution that is in Kazim, detailed in the Field et al. Paper. Next, please. So this is what it looks like. It's not very scary. Next. So what we've got here is the PSD, and then we've got some shape parameters, and this D is the diameter of particles. So this N0 is an intercept parameter that depends on mu and lambda. Next. Mu is a fixed value which varies by hydrometeor species, and this is prescribed in the model. Next. And then lambda, which we can calculate using a ratio of some physical properties about the particle concentration. Next, please. Okay, so this is quite an important bit, so we're just going to spend a little bit of time thinking about this, because this is really what shapes, this is what makes sure that the PSD is accurately described, accurately matches the observations. Yeah. Next, please. Okay. So these graphs, as inspired by Rob's thesis, just gives a representation of what changing each of the shape parameters does. So to make these, I have fixed two of the variables the same, and then we change the third one just to see what it does. So this is the effect of changing n, where mu and lambda are kept constant. Next. And then you've got the effect of changing lambda, where mu and n are constant. And next. Then you've got changing mu, where n and lambda are constant. And so the way I like to think of these is that n changes the area under the graph, lambda changes how sloped it is, and mu changes how curved it is. Yeah, next, please. So how to choose the right shape parameters. So particle concentration, n, is easy. That's an observed variable, so we just get that straight from our data set. Lambda is calculated using a ratio of observed variables. So that one's quite easy as well. And then we need to choose the appropriate value of mu from the model described in this paper. So next. So this is the 5 hydrometeor species they define in the paper. So we've got cloud, rain, ice, snow, and whirlpool, which are given these different values here. I appreciate this is not a very exciting table, but there's one crucial difference, and it's this one, snow. Because we've got quite a lot of snow in Oz, but how do we know that the one for snow is an appropriate one to use? So next, please. To do this, we can use circularity data, and this comes from the optical array probes once they've been post-processed. So the particle images can be processed to give each particle a circumference. So you can see in these two particles I've circled here, you can see that this little liquid droplet is pretty circular, whereas this ice crystal is much less circular, although that is not the worst example I could have picked. And then the circularity is proportional to the particle area divided by the circumference squared. So you can see this is going to be fairly close to 1, and this is going to be less than 1. So next, please. So yeah, liquid has a high circularity. Ice normally has a lower circularity. There is some exceptions to that. When you get large aggregates that are, especially if they're photographed at a certain angle, they can look very circular, like this might do. Also heavily rhymed particles. So I'll explain what rhyming is in a bit, and yeah, I'll come back to that. So we are able to tell, if we look at all our circularities for all our data, we see that there is a very high proportion of particles that have a very low circularity. So we can be very confident that most of that is ice. But what's the difference between ice and snow? That purely lies in size. For reasons I will describe later, we are neglecting all particles that are less than 100 microns. And in the field at our paper, then they say that ice begins to convert to snow at 50 microns. So we assume that by 100 microns, it's all snow. Yes, next, please. So practical considerations, there are always some of these when you're working with observation data. Next, please. What is the circumference of this particle? There isn't a right answer to this. But it's one of those cases where this is a fairly small particle that's been observed with a probe which has quite a coarse resolution. So you can see it's very pixelated and very blocky. But if we just worked it out from that, that would give you something which is not a fair representation, especially if you get a little tiny particle where you'll get a circumference of 4 and it will be nowhere near 4. So that's something we have to think about. We have to sort of just take that into account. Next, please. What is the shape of this particle? So this is an effect of the optical array probes when it images the particles. Depending on how close to one of the arms the particle is, it can look more or less out of focus. So when it's pretty much equidistant from both arms, it looks like that, and you get a really good idea of what the particle shape is. In this case, we've got a nice polycrystal. But then you see when it moves closer to one of the arms, you get this diffraction pattern, and you start to lose the shape of that particle. And then you can see when it's really close to one of the arms of the probe, you lose all definition, and it looks circular. So that's something we have to be very aware of, especially with the smaller particle sizes and also with the coarser resolution probe. So we tend to do this kind of processing on the higher resolution stuff. Next, please. So kind of last bits to take into account. Some data correction techniques were implemented on the data before I got hold of it. So particles with inter-arrival times of less than 1 microsecond have been removed. And this is because when the plane flies through the sky, it crashes into ice particles and shatters them. And if it happens to be, say, the arm of a probe that shatters this particle, that could all go through the laser and you record it all, like we see in these examples. But we can tell by looking at that should have been one ice particle. But if you just sort of apply the processing, then it will count them all as individuals, and you'll get erroneously high concentrations of really small particles. So that's why this has been applied. So you get that one and you lose that, which is fair. And then we have neglected particles less than 100 microns. This is due to a response of the instrument. At really small particle sizes or at the top end of its range, there isn't a great enough sample volume of that size of particle to get a fair representation. So it gets this like response curve, which gives you erroneously high concentrations. So to make that problem go away, we just neglect them for now. Next, please. Okay, after all that, let's have a look at some results. So my research questions to start with. Does the PSD change shape at different temperatures? How do observations compare to model parameterizations in different microphysical regimes? What causes the difference between the observed and the parameterized PSDs? Is a bit ahead now. And what is the effect of inaccurate PSDs on forecast processes, rates, and forward modeling observables? So let's start with the first one. Yeah, and again, please. This is an average PSD per run measured by the 2DS probe and the HPPS probe. So the 2DS probe measures just those like small particles, and then HPPS can measure up to 20 millimeters, but we don't have anything that size here. So on your x-axis here, you've got the diameter of the particles, and on your y-axis, you've got the particle size distribution. These units look a bit odd. Basically, it's because when you've got a probe with a much coarser resolution, you'll just get more particles because it's bigger and it can record more things. So we normalize it by the bin width to make it representative of sort of, it's almost a concentration per unit resolution. So what we can see here is the particle size distribution does range quite a lot between different temperatures. So we're going from -28 at the top of the cloud here, down to 1 degree at the bottom of the cloud. And you can see at the top, you've got these very narrow distributions, pretty uniform. And then as the temperature warms up, they start to get much broader. They start to get different shapes in them, like this and like this one. And you start to get a lot more width until you get to above freezing, and then the snowflakes melt and become a smaller raindrop. Yeah, so next, please. Next question, next, please. How do observations compare to the model parameterizations in different microphysical regimes? So, next, please. Red here in this case is the parameterized PSD, not yeah, they've changed color for some reason. We're not using the 2DS data here just because it lines up very well with at the small temperatures with the HPPS data. So it's kind of easy to just use one set for now. So we can see that the parameterized PSD does a pretty good job in some of these images and a much less good job in other places. So again, in these kind of pretty uniform, narrow distributions, it does very well. And then you get to about -12. And it gets to start very well, and then it gets to tail horribly wrong. And that is a pattern that you see in all of the rest of them, really. So it is not well capturing how broad these distributions have got. Okay, next please. So let's have a look at what causes the difference between the observed and the parameterized. So next please, a little bit of more background information. Particle habits. So that's just the shape that the particle grows in, and they grow in different shapes depending on the temperature of the environment that they form in. And some of these have very specific regimes, which is great because it acts as a signature as to where it formed in the cloud. So things like these needle crystals grow in this very specific region, about -3 to -8. Dendrites, especially bigger dendrites, grow in this kind of 10 to, I don't know if I'd say the gross was always 20, but this is someone else's plot. And then you've got things like plates and columns, which grow pretty much everywhere, but the key to those is they are low humidity. Okay, next please. Next bit of background is about ice formation. So at temperatures greater than -38, liquid droplets require an isonucleating particle to freeze. And these are insoluble particles that are found in the atmosphere. And they're made of dust, soot, ash, organic matter, the type of thing you can see here. Sorry, this cough will go away in a minute. Next, please. And we go. So then there's a few methods of ice nucleation to think about. And that first one is water vapor deposition. So your orange hexagons here are representing your ice nuclei. And these are your sort of liquid droplets. They're not droplets at this point, but yeah. So this deposition is when your water vapor attaches itself to your ice nuclei. Next, please. Then you've got contact and immersion freezing. So this is when you've got supercooled liquid droplets in your cloud, and those droplets come into contact with an ice nuclei, and they can either come into contact on the edge, and it will cause the outside to freeze, and it will sort of freeze inwards, or the particle can sort of move into the middle of it, and it will cause the droplet to freeze from the middle. Next, please. And then at cold temperatures, and cold being less than -38, you get homogeneous freezing, where it just spontaneously freezes if it's any liquid. So you don't tend to see supercooled droplets at colder than -38 degrees. Next, please. But we have a problem. Next, please. So for decades, we've observed that concentrations of ice particles in natural clouds are orders of magnitude higher than the observed number of ice nuclei. And this is like the concentration of ice is thousands of times higher than the concentration of ice nuclei. Next, please. So we've just said that homogeneous freezing does not require an ice nuclei, but it is not efficient enough to account for this difference. And it's also at temperatures that are much warmer than -38 degrees. Next, please. So where is this extra ice coming from? Next, please. Secondary ice production. I just like these images. Next, please. So this is a lovely diagram from Korolev and Leisner. This explains the sort of 6 mechanisms that we believe secondary ice production happens by. It's a bit of a controversial topic still. There's been a lot of debate for the last 50 years whether it is happening, whether it isn't happening. And even up to this year, there's been laboratory studies that show that it's not an efficient enough process to cause the sort of disparities we're seeing. But then it's fairly frequently observed in natural clouds. So it's an interesting problem that we want to look into a bit more. So we're just going to worry about droplet fragmentation and splintering during rhyming here. The other 4 mechanisms have had a lot less sort of research time put into them. Those are the best 2 researched ones. So the mechanisms here, droplet fragmentation. This is where an ice splinter or an ice nuclei comes into contact with the surface of droplet. The outside freezes, and as it freezes inward, the pressure inside the droplet grows, and it can shatter like it's doing here, and this can send out little splinters of ice. And then splintering during rhyming, this is where you have an ice crystal, and then you have supercooled water droplets. The supercooled water can come into contact with the surface of the ice crystal. They freeze on, and then in a similar way to droplet fragmentation, as they freeze and the pressure in the rhyme builds, it can send out these little splinters. Next, please. So it happens generally in this pretty specific region of -3 to -8 degrees. You have to have supercooled liquid water present for these 2 mechanisms, which then it produces tiny fragments of ice, and these act themselves as ice nucleating particles, which accounts for that difference in ice nucleating particles that are not ice. That's how the rest of the ice forms, if you like. So this is just an example image of some supercooled liquid droplets captured by the 2DS probe. Next, please. Also, it produces some pretty funky ice crystals. This is what I'm dubbing the rugby ball. And that's when the outside of a droplet starts to freeze, and then it cracks and the water tries to get out and it freezes, so it creates this kind of rugby ball shape. The ones that then form from the splinters often form into this kind of shape. We've got, this is a sort of hollow column. If you were to look closely, you'd be able to see that there's kind of a hollow triangle there and there. But we also see needles, which look pretty similar to that. And then the rest of these are what have been known in the literature as ice lollies. So this is where you get needle crystals, which then a supercooled droplet attaches itself to and sticks on it, continues to grow like that. But I think they're pretty cool. So next, please. So with all of that information in mind, we're now going to have a little look at some examples of what might be causing the differences between this parameterized and the observed PSDs. So looking at a good example to start with, you can see that here the parameterized PSD pretty closely follows what we see in the atmosphere, which is great. So next, please. If we have a look at the particle habits from the images that we see at this time and temperature, we see mostly these sort of polycrystals, and they're pretty uniform in size, and it's all pretty much the same habit, which is why you're only seeing these particles up to about 2 millimeters. Next, please. So to look at a less good example, next, please. You can see here that the range of particle habits is much greater. So we've actually got quite a lot of supercooled water at this temperature, which isn't really affecting the PSD all that much because it's all pretty small. It's all less than about 150 microns, which means it's only really being counted into this first size bin. But then the peak you're seeing here is a lot of these plate crystals. And then as it all gets bigger, you can see that there's a lot of dendrites being formed, which these are both crystals that you would expect to form at this temperature. So it's kind of important that the parameterized PSD is able to pick that up. Next, please. So then this is an example of what we think is secondary ice related. So crucial feature on this one is the fact that the smallest size bin is not, it's the highest, it's got the highest concentration of ice crystals, whereas most of them have done this sort of curve. This one starts high and drops off. And when you look at the particle images again, it's needles you see, so we think they've grown from splinters caused by rime splintering or droplet fragmentation. And then when you look at these bigger sizes, you see more dendrites. And now you wouldn't expect dendrites to be forming at this temperature. So what that means is they have formed at higher regions of the cloud and precipitated into this layer. But again, because the model makes no distribution between different particle habits, it needs to be able to pick that up. Next, please. Okay, yeah. So that's kind of why they're not matching up very well. So what's the effect of that now on forecast process rates and forward modeling observables? So next, please. I've picked two to have a look at, which is precipitation rate and radar reflectivity. So we have an absolute difference in dBz between the observed radar reflectivity worked out from the observed PSD and then from the parameterized PSD. And then we've got a percentage difference in precipitation rate. So what you can see on both of these plots really is that at the colder temperatures, it does a pretty good job. It's overestimating a bit, but it's not much. And as the temperature warms up, you see this, you get to start to see this sort of failure down to about 25% here. And we've got one that's like getting the rainfall wrong by up to 50%, which as a user on the ground, that's the bit I think you care about the most. Yeah, we'd like to be able to sort of try and fix that. Next, please. Okay, limitations. Firstly is that we're using a singular case study. There are more case studies from this field campaign, but also other field campaigns that it would be great to perform similar analysis on and see if we're seeing the same kind of things or whether it varies a lot by location and different temperatures and types of cloud. The other thing we've done here, we've got an average PSD of quite a large spatial scale. So what I mean by that is each time the plane does this, it records a run, and that's about 50 kilometers. And we've sort of averaged the PSD over that 50 kilometers, which obviously we know a cloud can change quite a lot in that kind of region. But the reasoning for this was to get a decent sample of all the particle sizes, because if you go for a space that's too small, you don't get a good representation of like particularly the largest and the smallest particle sizes. So the further you keep going, the better your statistics are. Next, please. So summary and conclusions, I guess. PSD width depends on temperature due to its effect on particle habit and also secondary ice. The suitability of the gamma distribution to represent PSDs also varies by temperature. What we have thought would be a good thing to do for the ones that sort of aren't fitting very well is try and maybe fit two gamma distributions and sort of break it up a bit more by habit and by process and see if that makes a difference. But as a result of this, radar reflectivity and precipitation rate are also inaccurate. because of inaccurate PSDs. Oh, I had images there, but it doesn't matter. They're not important. Next, please. So a little bit about future work. Our sort of immediate future work, we're writing this up into a paper, but once we've done that, we want to look at further investigation in secondary ice processes. So in which regimes is it most prevalent? Which mechanisms do we see? I think that could be a really interesting avenue to explore. And do we see it in other case studies? And there's some other ideas down here, including sort of how we're handling the data. So averaging over short time periods, splitting the data into liquid phase regions and ice phase regions, and different particle populations. And then a sort of longer term aim, test more case studies, including a range of cloud species. I think that could be really interesting. Understand whether parameters could be changed in order to better capture the observed PSDs in these cases. So that would mean you wouldn't be able to change the values of n because that's an observed variable, but changing the values of mu and lambda that you can use to, I've sort of had a manual play with those, and I think it could be something we could do there. And also assess the impact of this on remote sensing retrievals such as radar. Next, please. Oh, yeah, that's just a little list of my references. Next, please. Thank you for listening, and I'm happy to take any questions.
Any questions in the room first? Let's see if there's any online.
Yes.
I have a question. If you have some suggestion for the relation between the optical diameter of particles and the physical diameter or the physical size.
Yeah, so it's an interesting point and one that I haven't spent a lot of time thinking about because there's sort of not a lot I can do about it, but the diameter is sort of measured at whichever angle the particle came into the array probe, which for a lot of the small round stuff doesn't matter too much, but I appreciate like if you get a needle and it's that way, then your diameter is going to be quite a lot longer than if it comes in that way. Yeah, it's something I need to think about and at least acknowledge as a problem.
I didn't need a collision diameter, I mean the optical one. It's like when we are dealing in models, this radiation diameter of ice particles, and sometimes the issue is that like you have particle of some shape and how to actually estimate the relative effect of it. That would take the optical size of it the same as a collision one or different one?
Right, I'm with you. Yeah, it's something we are going to start looking at hopefully this coming week.
Okay.
Yeah. Yes.
When you fit, you've got your observed distributions,
Yes.
and you fit your red line. They were blue, and you fit. Presumably you're doing that for moments to do the fit. So
yeah.
What moments are you using, and is there a specific reason? Because you can basically use any set.
Yeah, and again, that is something we've sort of thought about. So we are using M0 and M2. So for people that aren't Rob, that's number concentration, and the second moment relates to the mass mixing ratio. So we're using the ratio of those just because that's what Kazim does, and that's what most forecasting models would do. However, again, I've had a play, and it would be really interesting to use some higher moments because then it would fit that tail of the curve much better.
It's really, I mean, I've done similar things on rain, and it's difficult to know which ones to choose. You kind of have to pick ones for a physical reason because otherwise Wales. So like M0 makes sense; it's the number of them.
Yeah.
M2 is kind of an area.
Yeah.
So yeah, weirdly, I ended up using M's 3 and 4 because rain is about 3.5. Okay. So if I use 3.5, 3 and 4, it roughly equated to being rain.
Yeah, I would quite like to use M6 because that's
it's reflectivity.
Reflectivity, and I just think that would. At ICCP, I saw a really interesting talk by a woman from Caltech where she was using like sort of overlays of like different moments to accurately capture her distributions, and I think that's exact. Can you go back to my like big worm plot?
It's probably worth saying for everyone else the danger of using M6. Basically, the higher you go in the moment, the fact that your Poisson errors from really small counts of the big stuff matters more.
Yeah. What we'd love to do on something like this is, because you can see the M0, M2 is actually getting that first bit really well, but we then like to be able to do sort of a different pair of moments, and that's where something like M6 will come into it, so sort of capture that bit and join them together somehow.
I mean, I might be going too far, but it does feel like you've got enough points, so you could probably do an optimal estimation settle back quickly based on 4 parameters, 2 different gammas.
Yeah, that would definitely be interesting to do.
That would, I mean, because it's not going to take long. It's not. You've got plenty of data points that you can fit 4 unknowns without too much trouble fairly well, I would have thought.
Yeah. We'll have a think about it.
Any more questions in the room?
Yeah, I'm not sure if I understood the presentation towards the end when you compared the radar. You seemed disappointed in the results. I'm not sure. I thought they looked pretty amazing.
Yeah,
I think I agree with you, by the way. As a massive radar nerd, I think I agree with you.
Maybe
They are
I don't
largely
understand
amazing.
radar enough. Because the rainfall one where it was estimating wrong by like 50%, I think is pretty poor, and I guess.
But I think that's because, as you were just saying with your moments problem,
Yeah.
you're only fitting half the spectrum.
Yeah. No, that's exactly what it is, isn't it?
So it's got
that one
50% of the
especially-
rain because it's got 50% of the rain.
Yeah, and that one especially is really
and it's
poorly
ignored the
fitting.
entire rest of the rain,
Yeah.
and so it hasn't got it.
Yeah, and that's where it'd be really cool to like find a better distribution and then test it again and see how good it is.
I thought about commenting on the fact that actually your ones that fit really well, and I've put that in air quotes, they do fit really well, but they're not perfect.
Yeah.
And you can tell they're not perfect because they're a bit too high, and they're
Yeah.
all a bit too high.
Yeah.
Now, I'm not going to go as far as to say they could, but like, why? Basically, I mean, is it? Yeah, you're comparing the Cassine version versus. Is it just that the Cassine mu value is wrong?
When you put,
And
you put other values in mu and it works better.
yeah, I mean, and I've done enough over the years to know that mu does not stay the same.
Yeah, and I think that's where we're sort of going perhaps with a thesis part, is some sort of practical.
Your lovely table of 2.5s or 2 for mu, does it include rain?
Yes, rain
Yes,
is
it
also
does.
2.5. Yeah.
Yeah, rain is 2.5 because I think 2.5 isn't high enough.
Yeah, I would probably agree with that. Yeah.
So I would say somewhere around 4 or 5 is about right for rain.
Yeah, we don't have enough like rain in this to test that, but that's where looking at a different case study would be good because there's probably one with more rain in.
I mean, I've got plenty of theories that the gamma distribution doesn't work either for rain, but we have to assume something, and we can't go 6 parameters. So
No, indeed. But I think some sort of practical recommendation as part of a thesis is kind of where we're going, and hopefully being able to recommend some parameters that work slightly better, or at least
I think
a bit
you've got
more of the time.
observational. I mean, you've practically got observational proof that you have 2 different gammas going on at the same time.
Mhm.
I mean, they look like there's 2 gammas stuck together.
Great. I'll just see if there are questions online. Any questions in the chat? Yes, there's 3. Okay. I'll just read them out because I'm not sure if they're allowed to actually speak because it's webinar. Will collision and coalescence be possible to include in models according to the wind environment on a particular occasion?
An excellent question that I don't know the answer to.
Okay, Len, great question. Declan says, thanks, great talk. Did you see any grapple in your case?
Not surprisingly little. I've looked through a lot of these particle images, and while we see quite a lot of roaming, we don't see much in the eye grapple. So no, not really.
Very good question, Declan. And then Brian, some modelers are going for bin models. Can that be done in a way that deals with the shape problem?
Again, I'm sure it can, but I would need to have a think about it more to be able to answer that.
Can you explain what a bin model is?
Sorry?
Can you explain what a bin model is?
Well, no. I do know what it is, but yeah, it's hard to explain. Yeah. No.
I think the answer to Len's question is going to depend a lot, because it's going to be incredibly based on turbulence as well, on how much they're going to collide, etc. So
Yeah.
turbulence is not exactly an easy thing to get right.
No, indeed. And we have, I think we have like vertical wind measurements from our flight.
Yeah, you
So
will.
yeah, it's just not something I've ever looked at, I suppose.
Great. Any more questions online? Maureen? I've got two quick questions. For more case studies, are you possible to use Westcon? Is that in the works, or is it more Picasso?
I think I would be sticking to Picasso mostly because it was very sort of much focus on microphysics, and my supervisors were two of the lead people on it, which helps. Whereas neither of them were particularly involved in Westcon. But as a future project, also using Westcons, so some sort of an entirely different time of year and types of cloud would definitely be very interesting. Yes.
And the second one was all about.
Wait.
Rob, do you want to go?
Yeah, well, I was related to the Westcon question. What kind of weather? Well, it was all frontal, wasn't
There's
it?
a lot of frontal,
Do you
yeah.
think going into Westcon, which would be very much not frontal, it would be definitely convection?
Yeah.
It actually might be the way to go, just to get something totally different.
Yeah, no, it would be very interesting. And there was another one that I can't remember what it was called now, but that dealt with like cirrus clouds. I'd quite like to look at something like that as well, and to just get an entirely different type.
I'm just thinking that there will be cases where there's fairly meaty, I'm going to go for, like wide runs through through what is convective. They're not going to be. Whether you'll get 50k run through a cloud that's
It doesn't have to
convection.
be 50. It's just that's what I've got. Yeah.
Yeah.
But
It might
you see
be
a
more
bit more gravel
difficult,
then
but
as
you
well.
won't have them straight towards the radar very often. But
Yeah, I haven't used the radar all that much at the moment.
it is something that we did at
yeah.
times, but it wasn't
Yeah.
very absolutely what we did every time. So.
Yeah. Okay. Interesting thing to think about, definitely. Yes. What was your other question? Oh, sorry.
Just with the benefit of many decades hindsight, it is extraordinarily difficult to get the aircraft, the airspace, the radar, all there on the day with the right cloud.
Yes.
It's been going on for decades. And I think from what I've seen, you've made some really good progress with this data set.
Thank you.
Congratulate you.
Is this one of the cases where you can actually see the plane in the radar scan?
Yeah, it's got the black streak in it. Yeah.
Yeah, they're so carefully aligned you can actually see the radar, the plane in the radar all the time. So
that was always the intention.
Yeah, you pretty much got it nailed doing that with Chilbolton now, but it's even now you do miss sometimes.
What was your other question?
My other question was, why is there such a big debate on the secondary?
Yeah, it's an interesting one. Yeah, just because throughout the last kind of 50 years, people have continued to find it's there and also not there. And from what I've read, I want to say that's because it's the difference between lab experiments and a real observed cloud. But that isn't always the case. People have been able to reproduce it in a lab.
There's an awful lot of lab experiments that come up with results that you think that's a bit weird and the real life won't do that. And for decades they get ignored because people think it can't possibly do that. It's the wet hail. When you freeze hail, there was an experiment back in the 80s. I can't for the life of me remember who did it. And basically they had photographs in the lab of the water on the hail particle turning into a donut around the outside of a roughly spherical hail. And you think, no way does that really happen. And yet now we have radar observations where the only way we can really explain them is with a donut of water around the middle of around an ice core. And how the hell could that? And suddenly this piece of work that was done 30, 40 years ago that everyone ignored because it seemed ridiculous is the only way we can explain the observations that we get now.
Yeah, well, in '74, Hallett and Mossop did their first sort of secondarized paper, and that was a lab experiment, and they showed it worked. But about a month before, there was a paper published by Mossop which showed it didn't work. So it's kind of been that all the way through. And earlier this year, there was one published where they were like, there's no evidence for an efficient secondarized mechanism, and yet something is causing these massively high concentrations when we're not seeing the isonuclei. So yeah, it continues to be exciting, and I'm kind of excited to get involved with that bit.
And presumably that observation of massively more ice than there should be is by numerous different ways of measuring it. It's not because like the shattering was something that for a long time has been are we actually measuring things wrong because everything's shattering, and so we're getting hundreds more and they're much smaller than we think they should be?
Yeah.
We're so much more aware of the problem now that, I mean, you showed beautifully an example of, yeah, just get rid of these because they're clearly wrong.
It is, I feel with observations and especially stuff, slightly experimental stuff like that, you always are kind of thinking like, oh, is this just an artifact of the instrumentation? But with secondary eyesight, I really don't believe it is. I think those processes are happening. There's some I don't believe in as much as the others, but
I mean, it's different enough. The radar observations wouldn't make sense and so on if it wasn't real. So.
Great. Any more questions? Can we finish? No? Thanks so much, Rosie. Big round of applause. Thanks everyone for joining online, and we'll see you at the next one.